And so yeah, so I'm going to talk about some recent work about semiconductor Moiré superlattices. This is what motivated us to look into these strongly interacting systems in 2 dimensions. And in the end, we think there's some kind of interesting sort of theme that emerges from this. We basically can start with simple Mott insulating states in the semiconductor heterostructures, and we show that by doping and by what I call inversion, band inversion, it can give rise to other kinds of interesting phases. And also, the theory hopefully is more generally applicable to other systems. Even though what initially got us working in this direction is Moiré materials, you will see that the theory is more formulated in a more general way. So let me first acknowledge all the brilliant students, postdocs, and Margarita is now in 4th year graduate student at MIT, and Yang, Zhang, and Chita, 2 brilliant postdocs. I work on the theory of quantum materials and quantum matter, and by quantum, it can mean different things to different people. But here, we all know that at a very fundamental level, all materials are governed by the laws of quantum mechanics, because materials are made of atoms, atoms are made of electrons and nucleus, and electrons take a discrete state in an atom, and when atoms assemble into a periodic structure to form a solid, these energy levels of atoms hybridize and they form interesting electronic spectrum. And that macroscopic materials can also display novel quantum phenomena at a macroscopic scale, and the examples are the superconductors, which is a zero resistance state. It's quite remarkable. Shows up at low temperature. Another example is this quantum Hall systems, sort of electron gas in the magnetic field, and they can show very unusual emergent particles with 1/3 of an electron charge, for example. So I'm going to focus in this talk about some kind of a much more simple states of matter. I'm going to start with some very simple states of matter. These are the insulators. And insulators are basically states of matter with an energy gap, so that it's difficult to pass current through the system. It's difficult to perturb the system and to make a change. In order to change the state of an insulator, you have to supply a lot of energy to overcome the energy gap. So this can be sort of as a defining feature of an insulator. It's a state of matter with an energy gap. And there are, broadly speaking, 2 classes of insulators in quantum condensed matter physics. There's so-called a band insulator, and there's a so-called a Mott insulator. The band insulators are formed when there's an even number of electrons per unit cell, and Mott insulators are formed when there's odd number of electrons per unit cell. And band insulators can be understood in a simple way. It can be understood already in the non-interacting limit, assuming these electrons do not interact with each other. As you can see that the energy levels of individual atoms, they hybridize to form the so-called energy bands, and the different bands are separated by an energy gaps. So each of energy level can be occupied by 2 electrons, one will spin up and one will spin down. So when there's an even number of electrons per unit cell, we can have a completely filled band, so-called valence bands. And then at the Fermi level, there's an energy gap between this occupied valence bands and the unoccupied conduction bands. So this energy gap is due to basically the single particle effects, the spectrum of electron in a periodic structure, of a single electron in a periodic structure. And together with the Pauli exclusion principle, which says that if electrons do not interact with each other, all we need is just to fill these energy levels up to the highest occupied state. On the other hand, the Mott insulators can only be understood through the electron-electron interactions. So with an odd number of electrons per unit cell, then in a non-interacting case, the valence band would only be half filled, and this will necessarily lead to a metallic state with a Fermi surface. But when there's a strong local repulsive interactions, electrons can organize themselves into a lattice like this. So here, these sites are the locations of the atoms, and you have basically, for example, one electron at every atom. And in this case, if you want to hop an electron to the adjacent sites, it will necessarily create a doubly occupied atom, and this can cause a lot of Coulomb repulsive energy. And that's why repulsive local interaction can lead to an insulating state. So regardless of whether we're dealing with Mott or band insulators, most of the insulating states seems rather simple. They can be understood by taking the following limit. Imagine that we trying to take apart the whole crystal by increasing the lattice constant. And when you ask how the energy spectrum of the system changes as this crystal is taken apart. So it turned out for ordinary insulators, or normal insulators, the energy spectrum, the energy gap at the Fermi level remains present when the crystal is being taken apart. And this is what we can call a normal insulator. An example is that if you take an ionic crystal, sodium chloride, which is just table salt, right? And imagine that you take the lattice apart from each other, increase the lattice constant, it just becomes a decoupled array of the sodium ions and the chloride ions, sodium 1+ and chloride minus. And both sodium and chloride has complete field energy shells, so there's an energy gap. There's an energy gap in that limit. Now, in the real crystal, the lattice constant is a few angstroms, but still the energy gap remains present. So throughout this deformation process, the energy gap stays finite. So that's why sodium chloride is diabatically connected to an atomic limit. So to use this mathematical phrase, we can say that sodium chloride is topologically equivalent to an atomic insulator. So the idea of topology is that you can smoothly deform objects, and there are certain properties that are invariant under the deformation. So it could be the topological property of a coffee cup, which has one hole in it, and the topological characterization of a donut, which also has one hole in it. And in this example, the number of holes is a topological invariant. The same way, we can use topology to classify insulators. And a atomic insulator is insulators which can be smoothly taken apart. As we increase lattice constant, the energy gap stays finite. On the other hand, one may ask, what about some non-trivial insulators? Could there be insulators topologically different from an atomic insulator? And if they exist, it must mean that as we change the parameters, as we increase lattice constant, there must be an energy gap closing and the reopening transition, separating the two phases. So you can think of this as some sort of an intuitive definition of topological insulators, that these are insulating states which cannot be taken apart smoothly. As we increase lattice constant, the energy gap has to close and reopen, so there has to be a phase transition from a topological insulator into an atomic insulator. This also means that different part of the topological insulator are inherently entangled. They are qualitatively different from the atomic insulator limit. So within the framework of band insulators, this actually really happens in real materials. So the first example of this kind of gap closing and reopening, so-called band inversion transition, that I can found is from 1966. It's actually a work done at MIT. Back then, people are interested in these narrow gap semiconductors for laser applications. So these two materials, lead telluride and tin telluride, they both have this rock salt structure, FCC lattice, consisting of a cation atom, lead or tin, and the anion atom, tellurium. And both lead and tin telluride have an energy gap. Okay, so these are all insulating states. But one can actually form an alloy, lead and tin and tellurium. Okay, so lead and tin can mix, form an alloy. And as a function of alloy composition, it was experimentally observed that the energy gap actually initially decreases and then opens up again. So back then, this was conjectured that there is this gap closing and opening transition, but its consequence, what is the consequence of this transition, was not understood. It was also not understood which of the two, lead telluride or tin telluride, is an atomic insulator and which one is what we now call topological insulator. So, so this was sorted out in about 10 years ago when we did the DFT calculations. And here I show you the band structure. And as you can see that at the low energy near the Fermi level, the bands have kind of a linear-like dispersion, just like the cartoon schematics from almost half a century ago. But there's something more we did. We look at the wave function, okay, of these states in momentum space. The red dots labels the size of the red dots labels the weight of the electron wave function on the tellurium atom. So if you look at the lead telluride, you see that all the occupied states below the Fermi level are coming from tellurium, the p orbital of tellurium. This is what you expect from essentially an ionic insulator consisting of lead 2+ and tellurium 2-. Basically, the electrons transfer into the tellurium atoms. In tin telluride, on the other hand, in most part of the momentum space, the occupied states come from tellurium, but just near the valence band edge, the occupied states actually come from atom tin, and the unoccupied states actually come from tellurium. So from this, we know that tin telluride is qualitatively different, is topologically different from an atomic insulator. It's not equivalent to the atomic insulating limit. So this is the tin telluride is topological insulator. And one can actually have a very unified theory of all these topological insulators by considering the vicinity of the topological phase transition, just when the gap is about to close. And in this case, if you combine the conduction band and valence band, you form a two-band model which has identical form as the Dirac Hamiltonians. Dirac Hamiltonian that describes electrons and positrons. Here, you can think of electron as like in the conduction band, and the positron is described by the valence band. You can think that way. Then that all the topological insulators can be understood in a unified way from this Dirac theory. And when the Dirac mass changes sign, the energy gap closes and reopens. So one side will be topological, the other side is trivial. So within this field theory, you don't know which side is which, but you know that there has to be a phase transition. There has to be a topology change. And also, if you think about the domain wall, spatial domain wall between a topological and atomic insulator, then on the boundary, this is exactly where the so-called domain wall fermions of the Dirac fermion appears. By solving the Dirac equation for this geometry where you have the mass changes sign, you get localized states on the boundary. And back to the case of the lead telluride and tin telluride. As I said, the lead telluride should be topologically trivial, so it should have no surface states on the boundary. And indeed, this is what photon emission observed. There's no states at the Fermi level. But tin telluride is topologically non-trivial, so it has to have a boundary states. And you see from photon emission, there are states with this linear dispersion showing up at the Fermi level. These are two-dimensional surface states. Yes. Right. Yeah. So I'm coming to this now. Yeah. So I'm not going into too much details, but basically by now it's understood that there are various kinds of topological insulators. The first example is this quantum Hall systems that which has chiral edge states, electrons moving in one direction on the boundary. And there are two-dimensional and three-dimensional topological insulators protected by time Roseau symmetry, as well as protected by crystal symmetry. And in the case of tin telluride, it's a topological insulator protected by the crystal symmetries. Again, I'm not going to any of these details. And all I want to say that there's a common feature of these topological band insulators is that they are understood in the framework of band theory. And band theory relies on the formation of electron waves. So it's crucial that the wave nature of electron is essential for the emergence of topological band insulators. Okay. On the other hand, Mott insulators seems to be an entirely different beast, right? So, this is a classic example of a Mott insulator is nickel oxide. It again has this FCC rock solid lattice structure, and again, this is a conventional Mott insulator. It's equivalent to the atomic limit. We can take the whole crystal apart so that in this whole process, the insulating gap remains. So in the decoupled limit, it consists of nickel ions and oxygen ions, and nickel 2+ has an odd number of electrons. Okay, so that's why this is a Mott insulator instead of a band insulator, but still, it can be understood from the point of view of electron particles. So Mott insulator is very much like a traffic jam, right? If you drive a car in Boston, you see this all the time. And basically, electrons, right, are tightly bound to individual atoms, and because of the local repulsion, it does not move. It does not move. So motion is prohibited. So this brings me to this fundamental distinction between Mott physics and topological physics, right? So topological physics relies on waves. Mott physics, at least conventionally, it's all relying on the particle nature of electrons. So one may wonder, perhaps they are so different that there is no direct path between the two. Right. So what this talk is about is our recent work with Yang Zhang and the Topological. We show that actually, starting from a very conventional Mott insulator on a two-dimensional triangle lattice, we can actually do something to it and to turn it into a chain insulator. Okay, chain insulator is a type of topological insulator with one-way moving edge states, chiral edge states. Okay, and moreover, this transition from Mott to chain insulator is continuous. Okay, so when you have continuous transition, it means that the two phases on both sides of transition are actually intimately related to each other. So it turns out that Mott insulator already has a, so to speak, has a gene to become topological. Right. So we didn't come up with this idea out of blue, but we're actually motivated by the experimental observations. So these experiments are done on two-dimensional Moiré superlattices. And the most famous example that started all this business is the twist bilayer graphene. Yes? Absolutely. I mean, to even start with a Mott insulator, the Mott insulator itself cannot exist without interactions. Yeah. So we have to start with strong interactions to be. The transition also requires interactions. So this whole Moiré business started from the discovery of strongly correlated states, Mott and activity in twist bilayer graphene, two sheets of carbon atoms, slightly rotationally misaligned. And there's really an enormous effort in this direction, and so many brilliant people working in this field, and I just really enjoyed discussion with them over lunch. And I found myself impossible to catch up in the field. So instead, okay, I've been last 3 years, I've been focusing mostly on these semiconductor heterostructures. So these are two layers of atomic distinct material, not graphene, but 2 layers of this transition metal, that chalcogenide semiconductors. And here, the 2 layers can be identical or can be different. When you have 2 different layers of materials, they have a different lattice constant. So in this case, even without any rotational twist, you can already form a lattice. Right. So that's what I'm going to mostly focus on. So the work that started this semiconductor TMD Moiré structure is this work by Alan McDonald. Yes.
So you want to interested in the twisting, right?
You can also twist, yeah, in homo bilayer. Yeah. But this talk I'm mostly focused on so-called heterobilayer. 2 layers are different.
So theoretically, then what would be the first order difference between the TBG and the TB?
You will see that theoretically the semiconductor heterostructures are much simpler to deal with. I think, yeah, you will see that. Yeah, you will see that. So, okay, yeah. When we started working on this field, it was not clear. The physics will be equally interesting, but it turns out. So I think this is a very interesting direction. Yeah. Yeah. So okay. So basically the idea is very simple. That if you look at a heterobilayer of TMDs, for example, WSE2 and M1SE2, So this is, in a sense, the simplest kind of Moiré band structure. So basically, electron in this system, in this particular system, the two layers have a band offset. So the valence band top in one layer, WSE2, is higher than that of the MOSE2 layer. So if you dope holes into the system, the holes basically live in the WSE2 layer. So what is the role of the other layer? Well, it's just to cause a superlattice. So when you introduce the two layers together, there's lattice mismatch, there's a superlattice formation. So structurally, the layer itself is corrugated in a periodic fashion. So it's corrugated in a periodic fashion. And because of that, the valence band top is spatially modulated in the WSE2 layer. And this is modeled by just a simple parabolic dispersion, okay, plus a periodic potential. Okay, so this is really a textbook example of solid state physics, right? So you have a kinetic energy, P squared over 2m, and the periodic potential. The difference here is that this potential is a long wavelength potential. It has a period of the Moiré superlattice, which is a few nanometers typically. And this mass is the effective mass of the TMD semiconductor. And in this case, the mass is actually quite close to the free electron mass, okay, which just turned out to be a property of the WSE2. So then, as we again know from solid state physics textbook, that if the period, the Moiré period is large, then the potential energy dominates over the kinetic energy. We are in a so-called tie binding regime. So basically, every potential minimum, right, it traps a localized state. So when you dope charge into the system, the charge are basically trapped into this potential minimum, but there are some small tunneling between adjacent sites. So this leads to a tie binding model on an array of quantum dots. And the potential minimum form a triangle lattice. So we get a tie binding model on the triangle lattice. Very, very simple. And when we take also into account the Coulomb repulsive interactions, we get effective so-called Hubbard model on the triangle lattice. So that's the proposal by Allen back in 2018. And then in 2010, two experiments came from the Cornell group, from the Berkeley group, that showed indeed when you have two doped charges per unit cell, there's a band insulator, there's a resistance peak. But when there's only one charge per unit cell, at half band filling, you also have a large resistance peak. So this is the Mott insulator. I'm going to call this at n equal 1. N equal 1 means one charge per unit cell. It also means a half of a complete band filling, which is at n equal 2. Okay. Now things can be more interesting because in these systems, the number of doped charges is controlled by electrostatic gating. So it can be continuously varying from 0 to 1 to 2, or it can be anywhere in between. So at 1/3 and 2/3 filling, right? So we can have a situation where the number of electrons is a fraction of a number of these artificial atoms, right? So so in this case, then you get an interesting situation that again, because of the strong Coulomb repulsions, you can get formation of the Wiener crystal states. Electrons can spontaneously crystallize into a periodic superstructure. Yes.
These are STMs.
These are the cartoons, but they are STMs. Yes. So this back then it was only done in some kind of a transport optical experiments. Or they can say that they are insulating state at 1/3 and 2/3 filling, and then the conjecture, which is very reasonable, is that these are just this kind of a Wigner crystal states. And since then, the Feng Wang's group at the Berkeley has done STM measurements. They literally see this kind of charge order pattern. Yes.
Maybe not the system where in these strategies,
yeah.
It's hard to capture these.
Oh, so you need a basic interactions beyond the local on-site Hubbard unit. So when I say the Hubbard model, I really mean extended Hubbard model. There could be on-site repulsion and nearest neighbor repulsion. So one thing we did actually in this work with Cornell group is that since this experiment, many more insulating states are found at other filling fractions, not just 1/3, 2/3, but also 1/4, 1/7, 2/5, 3/5, etc. It turned out all of these can be understood by just taking a triangle lattice model with repulsive interaction, and you just work in the limit where hopping T is 0. Yeah, and you can get all this. And there also will work by Una Kim's group. This can all be understood by repulsive charges, classical charges with repulsive interaction, extended repulsive interaction. Yeah, so
you have multiple sites per unit.
that's what I'm coming to. Yeah. Okay, so now, so far it seems everything's completely classical. Okay, maybe not as exciting, but even in this particular system, WS2, WS2, right? There's still quantum mechanics effects. So one of the key physics of the Hubbard model is that when you have one electron at every site, it's still electron has a spin degree of freedom. So spins can be fluctuating, and there could be spin-spin interactions between adjacent sites coming from the virtual hopping T squared over U process. And this has again been observed. So one can probe the amount of spin polarization by applying external magnetic field and using circular polarized light. So if there's a value polarization, the left and right polarized light will couple differently. So it leads to so-called magnetic circular dichroism. The optical response is different depending on the polarization. And so if you now look at the asymmetry in the response between left and right circular polarized light, so-called the Zeeman splitting, it gives you a measure of the Zeeman splitting of the exons. If you look at that as a function of applied magnetic field, you find that when you are in the Mott insulating states, the magnetic response is at low temperature is greatly enhanced, okay, by a factor of almost like 200 compared to the case without any doped charges. And also, this curve is very much similar to the magnetization curve. If you have a system of local moments when you apply magnetic field, when the magnetic field is larger than some thermal energy scale or it's larger than the energy scale associated with change interaction, then you get fully polarized. Then the magnetization saturates. So there's a sharp rise and then towards saturation. Right. So if you look at the slope around the zero field, that slope defines the magnetic stability. Plot magnetic stability as a function of temperature. Here you find a very nice Curie-Weiss behavior. Again, this indicates the presence of local magnetic moments. And in this fitting, there's so-called Weiss constant. This Weiss constant is actually negative. In this case, it shows that there's some small residual antiferromagnetic interaction between the spin moments. And that's again consistent with Hubbard physics. The Hubbard model physics, T squared over U process of virtual hopping will actually generate antiferromagnetic interaction. The neighboring spin referred to anti-line rather than line. So now back to the question. So far everything I've described seems to fit all nicely into this simple triangle lattice model. Yes.
Is the charge gap order U?
It's that's what I'm coming to. Yeah, it's the charge gap is large for sure. Yeah. Now there's question how large it is. Is it order U or is it order something else? That's what I'm coming to. Yeah. So far everything seems to be described by a very simple sort of called a Hubbard model on the triangle lattice. The idea is that there's a potential minimum on the unit cell, and when you have one electron at every site, you get an insulating state. In this case, if you want to add yet another charge, you have to create a double occupied sites, and that will cost energy U. And this is the standard picture for the so-called Mott Hubbard insulator. The insulating gap would be set by Hubbard U. On the other hand, we proposed from early on, again almost 3 years ago, that there could be an alternative possibility. That we found that based on our DFT calculation, that in many TMD heterostructures, including this WS2, WS2, we found that the potential, Moiré potential, has multiple minimums within one unit cell. There's a primary energy minimum in one type of a local stacking region, and there's a secondary potential minimum in another local stacking region, this MX and XM region. And also the energy difference between these two potential minimums, which we call delta, is small. It's on the order of a few tens of millectron volt. It's small compared to the Hubbard U. Okay, and in this case, then the physics is kind of interesting. When you start with the Mott insulator state, every primary potential minimum is occupied. Add one more electron. Instead of a double occupancy, the doped electron, added electron want to occupy the second potential minimum. They want to transfer into a different site in the unit cell. right? Different sublattice in the unit cell. Yes.
So U is like 100 MeV?
U is more like 100 MeV. Yes, yes, that's our estimate. Yeah. So this is another kind of a Moiré insulator that's called in the literature the charge transfer insulator. A classic example is actually this cuprit. In cuprit, those charges actually live on oxygen, even though the local moments in the Moiré insulating state come from copper. Right. So in this case, if you look at the energy diagrams, there's an upper and lower Hubbard band associated with the primary energy minimum that's separated by Hubbard U. The upper Hubbard band consists of doubly occupied sites. The lower Hubbard band are formed by holes. But then inside this big gap, there are low-lying states, so-called charge transfer band. These come from the secondary potential minimum, a second sublattice. So for a long time, what we are saying was completely ignored, and it's hard for us to convince experimenters that this is the case. But very recently, there's multiple experiments came and supported this picture. So even in this WSC2, WS2, in this original system, Xiaodong Xu's work showed that he looked again at this magnetic circular dichroism as a function magnetic field and the different fitting factors. So your fitting factor 1, you see this big contrast. It shows that basically there is a magnetic circular dichroism in the presence of a tiny magnetic field. That's what we expect from Moiré insulator. But then, interestingly, around the fitting factor 2, this strong magnetic circular dichroism also shows up, right? So this is something that cannot be understood within the triangle lattice Hubbard model picture, because at a fitting factor 2 in the triangle lattice, you have to double occupy every site. So then there will be no local magnetic moment at all, right? But this dichroism actually indicates the presence of local magnetic moments. On the other hand, if you take into account of this charge transfer picture, everything can be explained naturally. There are 2 sites per unit cell, and together they form a honeycomb lattice. So when you are at fitting factor 1, the charges all occupy the one sublattice, which has a lower energy. But when you go dope it above n equal 1, the dope charge now has no choice. To avoid double occupancy, it has to occupy the second sublattice. So when you dope it all the way to fitting factor 2, every site, both sublattices are occupied. That still leaves us with a magnetic moment at every site. In fact, there are more local moments than before, and that's why the circular dichroism signal is even stronger. Okay. So this also means that anywhere in between fitting factor 1 and 2, the dope charge transfer to another sublattice. So an n equal 1 insulating state is a charge transfer insulator. So here, the charge transfer happens within the same layer. It's associated with different regions of the Moiré superlattice of the same layer. And here, it's difficult to control the charge transfer energy delta. But then,
so when you put the 2, they form a collinear?
Collinear, I think so. Yeah. There's actually there's another system which shows similar physics, and there's a plot in this paper that shows that magnetic susceptibility actually goes down at low temperature, and that is consistent with formation of a collinear antiferromagnetic state. Yes.
Why is the data white?
White in between? Well, you will see this from the second part of my talk. Yeah. So yeah, it's a metallic regime. Yeah. Yes. The charge actually all live on the one layer in the system, on WSC2 layer. Okay, so now, so what's really interesting experiment came from last year on MOT to WSC2 again by Cornell group. And here it was found that the system shows a very interesting phase diagram, not only just the Moiré insulating state, but many other states. And the magic here is that you can actually, using an electric field, apply electric field between the 2 layers. And I'm going to show a phase diagram as a function of filling, doping as a function of electric field. And in this system, the Moiré superlattice period is actually smaller. It's 4.6 nanometers. So quantum mechanical processes are more important. These are far further away from the extremely correlated limit. So that's where things get more interesting. So I just want to say here, the role of electric field is actually to tune the charge transfer energy. And now it's between the 2 layers. Okay, in this system, we can tune transfer charge, not just between different regions of one layer, but actually transfer charge between the 2 layers. So this is a phase diagram. As a function of top and bottom gates. So along this line, we have the, yes?
Maybe just said this, but the bands are hybridized in this system.
Yes. We'll talk about it. Yeah, so here, So along these lines are at constant filling factor, constant density. So this is the filling factor 1, half band filling. Nu equal 2 is 2 charge per unit cell, it's complete band filling. So here, for example, and while along this line, we're changing the electric field, maintaining the filling. Okay, so at filling factor 2, at band insulator, right, we see there's transition from one kind of band insulator to another kind of band insulator, right? So this already reminds us of this gap closing transition between topological and atomic insulators. And indeed, that's what we found by the DFT calculations on MOT2 and WSE2. So the 2 layers again has a band offset. Yes.
Okay. So just to clarify, both the Mott phenomenon and the charge transfer phenomenon, so both include these 2 layers.
That's right.
The single layer is just a boring.
The reason the single layer is yeah. So, but it's an excellent question. So Mott physics happens when charges are still mostly in one layer, but you still need a second layer to introduce a lattice corrugation so that it forms Moiré bands. Yeah, Moiré band has a smaller bandwidth. If you have a pristine monolayer, the bandwidth is very large. It's like a few electron volt. Then there's no Mott physics. Yeah, that's an excellent question. So okay, so in this system, MOT to WS2, again, there's a band offset, but this band offset is much smaller. It's only 0.13 EV at the 0 electric field. So as we apply electric field, this delta can be further reduced. So this tunable charge transfer energy is key to the phase diagram. Yes.
How much further does it close? Do you actually ever get interference between those bands, or are you always just the top and low?
So as I say, by increasing electric field, you can get into a regime where this band start talking to each other.
They do.
And they hybridize.
Okay.
Yeah, that's right. Okay, so in the calculation, this is the same kind of calculation as many other groups have done in the field. What we do is we can actually first put the 2 layers together and optimize their structure. So then each layer are corrugated, and then we can take the corrugated lattice of one layer and remove the other layer. So we can look just at the Moiré bands formed in one layer in the absence of interlayer tunneling. Okay, why we want to do that is because the interlayer tunneling is a small perturbation in this system for reasons I'm not going into details. But this will help us analyze how the bands evolve. So again, so this is the band structure on the MOT2 layer, on the WSE2 layer. In both cases, you see that because of lattice corrugation, Moiré bands are formed, right? There's these mini bands separated by small gaps. Okay, and this actually can be fitted very well by a parabolic band in the periodic potential. Okay, that's essentially you get that. And the 2 different colors correspond to electrons of different spins. So all you need to focus on is electrons of one spin, let's say the blue bands. And you see that for downspin states of the top layer, the band minimum, the Moiré band minimum is at kappa point, while the band of the other layer, the band top is also at the gamma point, at the kappa point, yeah, at the same point, right? So when the band offset is large, this band is maybe a few tens of milli EVs above this band. But as I apply electric field, I can reduce the band offset, and then I can push this band from the second layer above. So eventually, the 2 bands are cross each other, and then they are inverted, right? Then the top of the second layer band goes above the bottom of the first layer band. Okay, there's a band inversion that happens by just tuning the potential difference between the 2 layers through the electric field. So in technical terms, electric field inverts the bands on the 2 layers. Also, now this calculation is done for the 2 layers combined. So there's interlayer tunneling. That hybridization actually leads to a topological band inversion. It leads to a Chen number within each spin species. So the 2 spins come from 2 different values, and they have opposite Chen number, right? So all this is basically a sort of a detailed example of this topological band insulator transition I showed in the beginning in the introduction slides. So the consequence is that when this band is complete filled at filling factor 2, electric field will tune the transition from a trivial band insulator into a topological band insulator, and that explains why the gap closes and reopens. Okay. Now the focus of this talk is about at filling factor 1. half band fitting. So here at a large band offset, when charges are all in one layer, this insulating state is just a Mott insulator. But as you increase electric field, when the charge start to occupy the other layer, you see that very surprisingly, unexpectedly, experiments discover a spontaneous Hall effect. At even at zero external magnetic field, you see the Hall effect appears, and at low temperature, this Hall effect becomes quantized, approaching this H over E squared. This is so-called quantum Hall effect. Okay, quite surprising. So this leads us to speculate that you start from a Mott insulator and you tune it into a topological regime. So maybe we can call that a topological Mott insulator, whatever it means. So also from the experimental data, it shows that the transition from the Mott into the quantum anomalous Hall state seems to be continuous. There's no electric field hysteresis. And the onset of the quantum anomalous Hall phenomena occurs at about 3 Kelvin. It's quite decent. Yeah, quite decent quantum anomalous Hall system. The data has been reproduced in several devices. So this leads us to think about so why a Mott insulator can continuously transition into a quantum anomalous Hall state. So this summarizes the essence of our theoretical understanding. So first, in the absence of interactions, we are dealing with a half band fitting, so the system is necessarily a metal. But once I include the Hubbard U, I can split this into a lower and upper Hubbard band, so the system can be an insulator. But the system consists of 2 layers. The Mott insulating gap U is large. The second layer states actually near the Fermi level. It's charge transfer band, right? So if I dope the charge into the system, the dope charge will live in the charge transfer band on the second layer rather than living into a doubly occupied upper Hubbard band. Okay, so this is the starting point of our theory, is a charge transfer insulator. And then we can further reduce the charge transfer energy. Okay, as we reduce the charge transfer energy, the bottom of the charge transfer band can dip below the top of the lower Hubbard band. And then the hybridization between the 2 bands will create a non-trivial gap. Okay, so this is very much like the previous band inversion picture, but the difference is that first, we're not starting from the non-interacting band structure anymore. Our starting point is this lower Hubbard band, which is formed through strong interactions. And second, we will see that the band inversion between the lower Hubbard band and transfer band is highly non-trivial. It's something beyond this free Dirac theory. Okay, so to just go through this, the state we start with is a Mott insulator on the triangle lattice of 1 layer. It has this 120-degree magnetic order. It is the canonical order states on the triangle lattice. Spins are in the XY plane and form this kind of a spiral order. And if we look at the quasi-particle, the holes, if I have holes moving in this Mott insulator state, it has its own band structure, which is what I mean by quasi-particle band structure. It's a band structure of the lower Hubbard band. And all we need to know is that the band, this quasi-particle band has a single maximum at the gamma point in the Brillouin zone, okay? So this is very different. I want to highlight again that this quasi-particle band structure is very different from non-interacting band structure, okay? Non-interacting band structure, the Fermi level would be in the middle of the band, while here Fermi level is inside the gap, and we only need to know the band edge, the behavior at the band edge. So now, for the unoccupied states on the second layer, because the second layer is unoccupied, the charge transfer band has a spin degeneracy, while the whole states on the lower Hubbard band is spin polarized. It's spin non-degenerate. So this creates an interesting situation that we are trying to invert a spin polarized band and a spin degenerate band. So what happens here? There's a fundamental asymmetry that is not present in the band insulator case. In the band insulator case, I'm inverting a spin degenerate valence band and spin degenerate conduction band. Here we have a spin polarized whole band and a spin degenerate conduction band. Yes.
Why do you need a magnetic topological?
Oh, just because the system has a larger unit cell. Yeah. Yes. That's right. Yeah, that's right. Yeah. So you can work in the enlarged unit cell reduced Brillouin zone. So I'm showing all these plots in the reduced Brillouin zone. Yeah. So yeah, all I need to know. Yeah. So you can this is sort of it's simple to write down a model like this, right, with this time magnetic order, and you will diagonalize a Hamiltonian with a 3 times larger unit cell, and you find that this is what happens. Yeah. Yes. Questions? All right. Yes, Juan. Yeah. I'm using quasi-particle bands. Quasi-particle bands. Yeah. So to me, it's important that there's a well-defined quasi-particles, and that is true for this AFM magnetic ordered model insulator. Yeah. There is. Yeah. But as you will see that in the end, the transition itself is described by a universal field theory that is independent of the approximation used to arrive at it. Right. So here, you can say I'm using mean field theory, but what I really need is just the dispersion of a single hole, right, at low energy in this magnetic ordered model insulator state. So, and here the only information I use is that it has a band maximum at gamma point and this spin non-degenerate. That's all I need to know. Yeah, so, and people actually have done serious calculations for triangle lattice 120-degree AFM order model insulator state and look at the dispersion of a single hole. It has a well-defined quasi-particles. Yeah. So the almost always if you have a magnetic order, you have a well-defined quasi-particles at low energy. You need a very exotic state to have no coherent quasi-particles. Yeah. It's not the case here. Yeah. Well-defined quasi-particles. Yes.
Is there statistics of the quasi-particle?
Say again.
Is there original independent of the statistics of the
steady state
fermion versus quantum?
So it's a fermion, yeah. In this case, yeah, it's a fermion. In this case, it's fermion because it's a, this is a pretty simple order state. But you can use mean field theory, but you can also, this is a very general argument. I'm asking questions. So what is the quasi-particle of a single charge, right? Charge E particle. Charge E particle. That's a fermion. Yes. Yes.
I guess the magnons. Yeah.
So I'm assuming, yeah, that's a good point. I'm assuming that this magnetic order parameter is frozen. I'm neglecting the fluctuations in the magnetic order parameter, which is fine. Magnons doesn't, even we can include magnons at the end once we derive all the theory, but it doesn't change much. Okay. All right. So okay. So then I can then focus just on the low energy physics, right? So there's a holes in the magnetic ordered model insulator. It has a band maximum at gamma, and then there are spin degenerate state in the other layer, and so combining all these 3 bands, we have a 3x3 matrix, and there's a single particle tunneling term between the 2 layers, and at the near k equals 0, their form is determined by symmetry. The symmetry of the quasi-particle band structure. I'm not going into details. It has a P-wave form factor. But importantly, we should also write down all symmetry allowed interaction terms. And an example is that there should be some repulsive interaction between opposite spin states of the minority layer, which are called the B layer, right? Because the B layer has a spin degeneracy, so naturally there's an allowed repulsive interaction between spin up, spin down states on the minority layer. You can write down other interactions, but it turns out only this interaction is potentially relevant in this process. So, so then I can analyze this long wavelength field theory, with a single particle terms and with interaction terms, right? So I can first deal with the case of when the interaction between the minority electrons when I turn off, when G is 0. This is what the band structure looks like. Before band inversion, I have a charge transfer band above the minority layer. The spin degenerate band in the minority layer is above the majority layer. But then at the critical electric field, these bands all touch each other. There's a 3-fold degeneracy. And then after band inversion, 2-fold degenerate band is now below the 1-fold degenerate band. So after band inversion, then this very interestingly, there's a quadratic band touching that appeared right at Fermi level. And this has to be the case because I have to always maintain the filling factor of 1 electron per unit cell. So we have a 2-fold degeneracy at the k equals 0 and the condition of 1 electron per unit cell, it guarantees that the Fermi level would be set right at the quadratic band touching point. Now, it's known from very early and beautiful theoretical work by Kivelson, Fradkin, Kaishun, and Hongyao, that if you have a quadratic band touching right at the Fermi level, it's inherently unstable to interaction effects. Okay, so there's basically you have a finite electron hole density states, and interactions can open up a gap in a similar way as a BCS instability. Okay, in 2 dimensions. Back then, they considered a model of spinless systems, so it's difficult to realize. And here, well, the nice thing is that we have all the right ingredients very naturally in this setting of inverting a Mott insulator, a charge transfer Mott insulator, because the 3 states I start with, right, the 3 bands I start with, 2 of them are spin up, spin down bands of the minority layer, and after band inversion, they appear right at Fermi level. So this degeneracy is associated with the spin degeneracy of the minority layer. Okay, so there's no additional degeneracy at Fermi level. So that's the difference of this system with quadratic band touching bilayer graphene. In bilayer graphene, there's both valley and spin degeneracy. So there are many more interaction terms and many more type of instabilities. Here, there's only one type of instability. Yes. That's right. It is protected by symmetry. So there's symmetry is a 3-fold rotation. So E means 120-degree order state. It's invariant on the rotation. When I combine spatial rotation and spin rotation, there's a 3-fold rotation. Also, there's a time reversal combined with a spin SZ rotation. So the spins are in the XY plane. So if I do time reversal, the spins all get flipped. But if you do a 180-degree rotation around Z axis, it comes back. So these 2 symmetries together guarantee that this 2-fold degeneracy is protected. Okay, so basically quadratic band touching is unstable to interactions. So interactions open up a gap. So there's additional basic symmetry breaking. The electrons that are transferred to the minority layer get spontaneously spin polarized with spin polarization in the Z direction. So this happens only after band inversion. So before band inversion and at the critical point, turned out that interaction G is irrelevant. Only after band inversion, you get finite density state at the Fermi level due to this quadratic band touching, then interactions become relevant. It drives the system into this gap phase. And it's also known that quadratic band touching with a gap, this leads to a quantum non-small state because of the barrier curvature. Yes?
If you stack graphene, it's quadratic band.
That's right.
Split into 4 direct columns by.
Yeah, here it's completely robust.
I see.
Yeah.
But there's also the CP.
I think that's just because it's not at the gamma point in the Brillouin zone, it's at the K point. So this other symmetry I said, time reversal followed by a SZ rotation that is absent. Yeah. So okay, combining everything, what we say is that basically throughout the band inversion process, the majority electrons, the electron on the majority layer, still have this AFM 120-degree order structure. That's the Mott insulator we start with. But after band inversion, the electrons transferred to the minority layer, they have spontaneous developed spin polarization along the Z direction. So we get a very unusual magnetic pattern. It's a non-coplanar magnetic structure, and there's an inherent spin chirality associated with it. So after band inversion, there's a change of magnetism from purely XY in plane to the one with a canted SZ component. And at the same time, there's a change of the Chen number. So these 2 things happen at the same time, which is very unusual. Change of magnetism and change of topology. Yes?
Why the transferred electrons have to develop paramagnetic, whereas in the other layer, you still have this.
In the other layer, you still have that is because all my low energy theory is based on this 120-degree magnetic order. So band inversion only involves a small change to the lower Hubbard band. So that's why the majority of electrons in the first layer still maintain the AFM order.
Yeah, but in the other.
In the other layer,
they have to develop their.
It's because there's an inherent instability. After band inversion, there's a quadratic band touching on the other layer if you don't take into account of interactions on the other layer. But once you take into account of the repulsive interaction on the other layer, this quadratic band touching will be lifted. Because there's instability. It's like the BCS instability. Once you have a direct interaction, right, metals will become unstable to a superconductor. Here, because of the repulsive interaction and quadratic band touching, the charge on the secondary layer will become unstable to spin polarization. Become unstable.
So that comes out
From the theory, yes. Yes.
And thing is breaks this C to C.
That's right. Yeah.
Right. So it's spontaneous.
It's spontaneous. That's why there's a change of mechanism. Yeah. So mechanism changes. Yeah. Okay. So this basically gives us a unified phase diagram that as I apply electric field, I can invert the Mott insulator and turn that into a quantum non-small state. The magnetic pattern is different and the topology is different. And so this provides an explanation of the experimental phase diagram, why the Mott transitions into the QH.
Yeah.
Yes.
So this kind of anomalous fall is kind of unusual because there's spin parameters, right? In addition to the order. So to detect that phase, it would be nice to also probe.
Yeah, I'm sure. Yeah, So one thing I want to emphasize, this is very different from other quantum non-small systems. So the first quantum non-small system observed is this magnetic doped topological insulator, and here, the magnetism actually comes from doped atoms like chromium or something, and these moments are basically classical spins, and they basically open up the exchange gap and to the topological electrons. That's how it becomes a non-small state. So basically, it relies on ferromagnetism instead of this non-coplanar ferromagnetism, non-coplanar magnetism I talked about. And also in this system has an even number of electrons per unit cell. So it's not really a banding, it's a banding insulator, not a Mott insulator, right? Also, in magic angle graphene, at least in some of the devices, you get a zero field quantized Hall effect, Chinese insulators. And there it's generally believed that these systems are basically fully spin and valley polarized. Again, unlike the one I talked about, where you have this, non-fully polarized spin and valley structure. So our theory is very, very different. And also, the theoretical understanding in the magic angle graphene is that this kind of a fully valley polarization only happens when the bands are topological to begin with, and it's sufficiently flat. While in the case I've described, the bands are actually quite dispersive. Bandwidth is 50 millielectron volt. And we start with a Mott insulator, which doesn't have any topological quantum number. So we actually using electric field to drive the transition. So yes, back to Unan's question. So one of the predictions of our theory is that the magnetism should be very interesting. In the Mott insulator state, it has this in-plane magnetic order, so without any SZ polarization. So circular dichroism only probes SZ, so it should lead to zero circular dichroism. On the other hand, in the quantum non-small state after the inversion, there's some finite spin SZ polarization, especially on the minority layer, but it's not a fully polarized. There's still substantial XY components of the spin in the majority layer. So then the SZ polarization should be finite, but not fully developed. It should increase with applied magnetic field. It should increase with increasing electric field. So that's so there's recent experiments from again Cornell, the same group, and they again use a circular dichroism to measure the spin polarization in this system. And basically, you see that in the before banding inversion, in the Mott insulator state, the signal is zero. So it's not a fully. This actually has zero SZ polarization, consistent with this 120-degree magnetic order. And after the quantum non-small phase appear, the SZ polarization develops on both layers, but it's not immediately fully developed. It keeps rising up as you increase electric field. Also, it keeps rising up as you apply magnetic field. right? So at the zero field, the spontaneous spin polarization is about only maybe less than 50% of the value at 8 Tesla field, right? So interesting thing is that when you apply a tiny magnetic field, you see the RXY is already quantized. So this y-axis has both RXY and MCD signal normalized to their value at high field. You see that at a very small field, the quantum Hall effect is already fully developed, but the spin polarization still keeps increasing. So that's consistent with having a partial spin polarization, candid spin texture. Okay, yes?
Yeah. May I ask a question?
Yes.
Oh, yeah, hi, thanks. So I have a quick question about the spin degeneracy in the charge transfer band.
Yes.
In the background of an antiferromagnetic order, why are they still degenerate?
Yeah, it's an excellent question.
Yeah.
So if you look at what I'm drawing here, right? So they're actually exactly degenerate at k equals 0, but not exactly degenerate away from k equals 0. So you're right that because of the two layers are hybridized, right? You already have a spin, some kind of spin degeneracy lifting in one of the layers. So generally, you would expect the spin degeneracy to be also lifted in the other layer, right? This is true except at k equals 0. At k equals 0, there is a symmetry, this 3-fold rotation symmetry, and a time reversal combined with spin S-Z rotation symmetry.
Oh, I see.
These two symmetries guarantees that there's a two-fold degeneracy. It allows a two-dimensional representation, essentially, at the band edge.
I see. Thank you. Yeah.
Yes?
So in the MCD data, so Mott's coverage first as a function of reaction to first go up, and
right.
That's because the spin becomes a
That's possible. That's one possibility. I mean, so our theory is really focusing only in the vicinity of the phase transition, right? So we really cannot say much about deep inside the quantum or phase. I think it's actually a very interesting question. What happens down here? Yeah. Okay, so let me quickly wrap up this this part of the talk. So basically now I want to draw some comparison, some parallel between the two types of topological insulators, right? In the topological band insulator, when you have an even number of electrons, but just simply inverting the band gap can change from trivial to topological, right? It's understood a long time ago. And this is described by a direct fermion with a mass changing sign. At the transition point, we have a linearly dispersing direct fermions, and their interaction effects is irrelevant. It's perturbatively irrelevant. So that's why free fermion theory works so well to understand topological band insulators. But now, after 15 years, we come to a complementary picture for Mott insulators at odd integer fitting, right? So I started with a charge transfer Mott insulator, where the gap is between the lower Hubbard band and the charge transfer band. The lower Hubbard band is spin polarized. The charge transfer band is spin degenerate. But then if I reduce the charge transfer energy, these two bands can invert with each other. So here we are basically inverting a many-body gap, because the gap, the insulating state I start with, the Mott insulator, this gap has a many-body origin. It's due to interaction effects. So in this sense, we can say that if you have an antiferromagnetic Mott insulator, right? If we can tune the charge transfer gap from positive to negative, you may be able to achieve a topological state, quantum non-small state, because the energy scale of the Mott insulator is high compared to the ferromagnetic insulator. There are very few ferromagnetic insulators around, but there are plenty of antiferromagnetic Mott insulator with large gap. So this may provide a path to find some high temperature quantum non-small systems. That's certainly something I'll be fascinated if this can be found. So basically, I'm showing that these two different phases are not so far apart as I thought to be. There's actually a pretty short path between the two, right? So this is what I found online. This is the shortest international bridge connecting two countries, USA and Canada. All right, so can I just use 5 minutes to go through the second part of the talk? Yeah. All right, so the other thing I want to briefly tell you a little bit about is this, instead of an inverting Mott insulator, now let's think about doping a Mott insulator. And deal with whole doping of Mott insulators. In this case, I don't need to worry about double occupancies. I can just work with a triangle lattice model, right? So this is a very standard triangle lattice antiferromagnetic Mott insulator. But now let's ask question: what if I dope it with some holes? And this work is done with like Ritter and with Yang Zhang, these two papers. Again, there's of course enormous amount of work on this doping modeling in the context of a square lattice Hubbard model that's relevant for high temperature superconductors. Here it's triangle lattice, and what got me interested actually is that in this system there seems to be in the Moiré system there's some new regime that's not possible to access before. So if you think about this model insulator as function with external applied magnetic field, the Zeeman field. At the zero field, you have a 120-degree magnetic order that I showed earlier. But when you apply a field, if the field is large compared to the exchange coupling J, we can fully polarize all the spins. Now, this is something not possible to do in cuprates because the exchange coupling J is quite large. So to fully polarize all the spins, to turn the cuprate into a spin polarized regime requires enormous field, not possible. But in the Moiré materials, in WS2 in this first paper, it was shown that only apply a 1 Tesla field, right, at 1.6 Kelvin, you can fully polarize spins. So there's a question about the energy scales. So this actually is comparable to what you estimate from the from the bandwidth. The hopping T is on the order of 1 millielectron volt. There's an effective U because it's high transfer insulator. U is a little bit ambiguous, but roughly if you take something like 40 millieV, you get a J of order 0.1 millieV. So above 1 Tesla, you should fully saturate. It's all very reasonable. So the question is then, is there something interesting when the spins are fully polarized? You might say it's just a boring band insulator. That is true, but now let's ask, what about if you dope the system with holes? Let's even ask question, what if we dope it with just one hole, right? We start with a Mott insulator with antiferromagnetic interactions, but in the external field, the spins are forced to be all aligned. And then we ask, what if I dope it with one hole? Now, if the external field is very high, of course, we just remove one particle and the spins of all the other particles are still aligned with field. But interestingly, we realized that there's a wide range of magnetic field between this H0, which is set by J, and H star, which is on the order of T. Okay, in this range of intermediate magnetic field, the ground state of a Mott insulator doped with a single hole. It contains doped with a single charge. It contains not only the original bare hole, but it also involves a spin flip. Okay, so spin flip, because I have external magnetic field, the spin flip costs Zeeman energy. But the system would rather do that. Why? Because the spin flip can bound to the hole to form a bound state, and that binding lowers the energy. It lowers the energy more than the energy cost of flipping a spin. Okay, so this only works in the
Maybe you can even realize a small fermion.
We will talk about this. I think you were talking about multiple spin flips. We didn't find it. Yeah, but we do find that one spin flip is favored. Yeah. So this is basically the energy spectrum, right? You see there's a whole continuum which corresponds to a hole and a spin flip that are away from each other, but then they form a bound state. They form a bound state, and there's a well-defined branch that's below the continuum. Now, the way I like to think about it is very simple. If you think about the spin polarized band on the triangle lattice, right? So basically here I'm just dealing with a triangle lattice Hubbard model, and I'm working with infinite U limit, right? So there's no double occupancy. So when you have external field, in the Mott insulator state, it's just a fully polarized band insulator, right? The single electron is all occupied. Now, if you want to introduce a doped charge, I can just remove one electron from the top of the band. But the interesting thing, the triangle lattice is a non-biparallel lattice. So there are two degenerate band maximum at K and K prime, right? So if I only remove a charge, it can be either from K point or from K prime point. Because of translation symmetry, it has a well-defined momentum. But now, if I introduce a spin flip, then the translation symmetry is broken. This removed particle, this hole, can be in a superposition between K and K prime point. And by forming a superposition, the general perturbation theory, it lowers energy by order T, right? So that's exactly what we found. Okay, there's a bound state between a hole and a spin flip. And if you look at the wave function of the bound state, it comes primarily just from this band maximum. Okay, so it's a purely kinetic mechanism because of the, sometimes people call this phenomenon kinetic frustration. Because of this mechanism, it leads to a bound state between the hole and spin flip. So we first found this result by exam calculation, and agrees with numerics, everything is good. And then after we wrote up the paper, we were told that actually there's a very nice work by Batista from 2018, which is basically the same thing. If you read his paper, the reason we did an extensive literature search, we missed it because the title doesn't have anything to say about spin polarons. It's called pairing from repulsive interaction. So the most of the paper is actually about multiple spin flips. So if you have a more complicated bound states, and you can get perhaps superconductivity, etc., etc. That actually was also my original motivation. But on the long, in this project, I actually found that a single spin flip is the only stable object, at least within this model. So I think our agreement results are in agreement. Batista, he actually need to put additional hopping terms, second, third neighbor hopping, in order to stabilize objects that involve multiple spin flips. Yeah. Okay. Anyway, so now, but one thing that in the context of Moiré superlattice, there's actually a way to detect these objects, which is what I think potentially interesting for experiments. So, we can look at the band edge. Yeah, the band edge. Right. So here, we have a Mott gap, right? A Mott gap. So this branch is doublon. When I add a particle into the system, I create a doublon, and the energy of the doublon increases with external magnetic field with a slope that corresponds to spin 1/2. And if I now dope a hole into the system at a very high field, this hole, we just have a bare hole, and its energy also increases linear with magnetic field with a slope corresponding to spin 1/2 object. But at the intermediate field, right, the hole like to spontaneously create a spin flip that is bound to it. So this object then has a higher spin, right? It flips one more spin, so it has a carry spin 3/2. And therefore, this object should increase the energy of this doped charge would increase with magnetic field with a higher G factor. The higher effective G factor corresponds to spin 3/2. So if we monitor the evolution of the lower and Hubbard band edge in capacitance or compressibility measurements as a function of magnetic field, we should see there's a kink in the slope, right? Associated with transition from a bare hole spin 1/2 particle to a spin 3/2 particle. And running out of time, let me just quickly say that, again, you can then carry out this analysis to finite doping, and you find that basically on the whole doping side, the field you need to fully apply the system keeps increasing. It's of order T. It's all coming from the kinetic energy process. While on the electron doping side, you basically get Nagoka ferromagnetism. So there's a fundamental difference between the hole and electron doping of the triangle lattice Mott insulator. And experimentally, if you look at the saturation field, this is at the Mott insulator states. As you go above the Mott insulator fitting, you see that the saturation field actually gets smaller, consistent with ferromagnetism. But on the whole doping side, you see the saturation field get actually higher and higher. Right, that's agreement with it. So at finite doping, naturally, if you dope one particle will form a spin polaron. If you dope two particles, naturally you have two spin polarons. So basically, at small hole doping, we expect there should be some dilute gas of spin polarons. And indeed, by doing exact ionization studies on small finite size systems, we see that the sort of ground state momentum as a function of the doped charges is all consistent with just filling a Fermi sea of these spin polarons. Okay. Also, because each spin polaron carries spin 3/2. So if you have a doping, the density of delta, it means that there should be a magnetization that is locked to the doping, right? So each spin flip removes a spin 3/2. So the total spin polarization is the fully polarized state minus 3/2 times doping. So this means that there should be a magnetization plateau, and this is exactly what we see that from the DMRG studies Yang did on the 3-leg system. And you see that over intermediate range magnetic field, there's a magnetization plateau below the fully saturated, fully polarized limit. There's also related work by Eugene Demler's group that's motivated by Quadratic studies. Now, again, one last thing I want to mention is that because spin polaron carries spin 3/2, very different from a hole, fundamentally different from a hole, these are really orthogonal objects. So at low energy, we have a Fermi sea of spin polarons, but not a Fermi sea of holes. This means that if you want to do tunneling experiment to add a charge into the system, there should be a gap, right? The degrees of freedom at low energy. The gapless degrees of freedom at low energy are not single particles, not just holes, but a charged particle that has a totally different quantum number than a hole. So if you want to just add a single particle in the system, you'll see a gap. So it's a very interesting case. You have a metallic state. It's conducting, compressible, but it has a single particle tunneling gap. So we can call it a pseudogap metal. Does it have anything to do with pseudogap metal in qubit? I don't know, maybe not. So, but I think it's an interesting theory that can at least be tested experimentally. The signature would be the first signature would be that there's a magnetization plateau.
But it would be a finite energy gap, not just a pseudo.
There's a finite energy gap, yeah. I guess what do you mean by pseudogap is like it suppresses, but
Yeah,
yeah, maybe that's the definition. Yeah, but on the other hand, the qubit, the pseudogap is at finite temperature. Here I'm talking about zero temperature. Okay, so I'm already way over time, but let me stop here and thank my collaborators again. Thank you.
Hi, can I have a question? Sorry, could you hear me?
Yes.
Yeah. So when you said that when you introduce a hole into your Fermi sea of and it wants to minimize the energy by flip a spin nearby, then is there a preference of any of the spin? Like there are 6 neighboring spins, right?
You mean when I flip a spin nearby, does it have to be exact nearby, or it can be 2 lattice constant apart, 2 lattice constant
I mean, like
apart?
which of the 6 neighbor that it chooses?
It's a superposition.
It's a superposition of all.
So yeah, this cartoon is maybe oversimplified, but what it really is that if I have a spin flip at the center, right, you can see that the wave function involves spin flips at all neighboring sites, as well as second neighbor, third neighbor sites, the superposition of all these.
I see.
Yes.
Thank you.
Yes.
What's the interaction that makes it for?
That's an excellent question. Yeah. Right. That's an excellent question. So we can always make it repulsive by adding a longer range repulsive interaction. Right. So now in the calculation, if we just deal with the Hubbard model, right, then it's for this particular model, there's a well-defined question: what is the interaction between the spin porons? And we don't exactly know how to extract that from the numerics. But one thing we did is we put 2 spin porons, for example, into a 3-leg ladder. Right, we want to see where the 2 spin porons sits. It turned out they sit actually a distance L/2 apart from each other. It's basically the whole system size is L, right, and they are actually apart from each other. So it seems to me that means that they are positive.
I understand it right. So there's your last part of your talk.
Yeah. But also the first part I'm dealing with always at the fixed fitting n=1, right? I'm not doping it.
Well, my question was, you did the same thing in that.
What do you mean the same? Oh yeah. If you're whole, yeah, okay. You can actually, yeah, excellent. Yeah, you can actually look at a zero magnetic field. If you have a single hole in a 120-degree AFM state, right? In fact, yeah, I should mention this. Yeah. You see, if I work with infinite Hubbard model, as I did in the second part of this talk, right, then the magnetic order is completely degenerate at the Mott insulator. Right? If J is 0, I just have complete local moments. You can ask in this case, what happens if I dope electron, right? Dope a hole, right? If I dope electron, it is known that single added electron will fully polarize all the spins. It's called Nagoka ferromagnetism. If I add a single hole, it's also known there's a work by Shastri. Yeah, in 2008, I think, it gave a strong theoretical argument. If you have a single hole, it actually also leads to a metallic antiferromagnetic state. It's 120-degree order state. We have some slides. Yeah. If you just add a single hole, you can get a 120-degree AFM state. Again, not through the J, because I'm working with infinite Hubbard model, then J is 0. But there's through the kinetic energy T, it actually can lead to a 120-degree AFM metal. This work by Shastri and collaborators. There's also a nice work by Ashton's group, actually, paper was published just this year. If you have a finite small density of doped holes, again, they found by DMRG study, you get a 120-degree AFM metal. So in other words, in the phase diagram that I showed, I didn't add a label here, but if I ask me what is likely phases, a zero field, It's this 120-degree lattice. That's what the field is about. Yes, the first part of my talk. Yes, exactly. Yes. Right. Yeah. So there is some. There's one question about that whether I think the experimental paper they were discussing whether the spin polarization on the two layers are parallel or anti-parallel and how it compares to theories. It's an excellent question. Let me just clarify that a little bit. The answer is somewhat nuanced. So let me first tell you what in theory, and then tell you what happened in the experiment. What I think is happening in the experiment, that you will see is complicated. Anyway, so in theory, the field theory I described, right? I started with the quasi-particle bands of this in-plane Manet order state and the spin degenerate state, right? So within the field theory, it doesn't really know anything about the canting of the electron in the majority layer, because the field theory only involves a small number of holes in the majority layer, while the spin ordering on the first majority layer is associated with all the occupied sites, not associated with empty sites. So this field theory itself does not directly tell you the spin polarization on the majority layer. All it says is that after band inversion, there has to be a spontaneous spin SC polarization on the minority layer. Also, we know is that for a given spin polarization on the minority layer, Chen number is fixed. So whether the spins on the majority layer, whether it counts parallel or anti-parallel, it's the same phase. So topologically, the same phase with the same Chen number. That's what I know for sure on the theory side. It's all the same. It's all the same. So they're back connected. So on the experimental side, things are also unclear, in my opinion. If I have a slide. Yes. Okay. So these are the whole measurements for the monolayer WSC2 for monolayer MOT2. So what they measure is as a function of photon energy. Right now, spin polarization is something independent of photon energy. It's a ground state property. But as you can see, the MCD signal is photon energy dependent. Some region is positive, some region is negative. So how do we relate the MCD signal to the spin polarization? It's not entirely clear to me. I've also talked with some theorists, and apparently even for monolayer TMD without any moire, for fixed photon energy, the MCD signal seems to also changing with doping. Okay, this is what I learned from actually talking to some of Eugene Daimler's postdocs at Harvard here. So in other words, I want to say that at this moment, there's no microscopic theory relating the MCD signal in terms of its absolute value to the spin polarization. Yeah, so we know that they have to be related in a sense that if it's no spin polarization, there's no MCD. Right, so that's why. But in terms of a sort of an absolute relation between the two, I think it's not really present at this moment. Yeah. That's right. Yeah. Yeah.
It's a question about the direction of this axis on that.
That's right. Yeah. Yeah.
How the
That's right.
The polarization affects the sector, which is depends on the interactions.
That's right. That's right. Yeah. 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 I think there's actually a lot of interesting questions over there. So it could be interesting. And in fact, even monolayers, yeah, even monolayers, there's this known result that as the doping density increases, the MCD signal reverse sign. Yeah. While we don't expect the spin polarization to reverse sign. Yeah. So there's a lot of things that are unclear at this moment, I would say. Yeah.
Yeah, how about this CD? So in the spin power battle
yeah.
phase, the associated spin is very hard.
Yeah.
Measure the space?
I think it's easier to measure the space by compressibility measurement. Yeah, because compressibility is a ground state property, and if you look at how the lower and upper Hubbard band edge changes with magnetic field, this is the kind of experiment that for example, like compressibility scanning, SET, compressibility measurement, they do this measurement all the time. So these are all ground state properties. So yeah, so how the energy gap, for example, changes with magnetic field, is there changing slope?
So
yeah,
this is principle can be realized in the MOT to WSC2.
I think it can be like many.
Yeah.
So including also the MOT WS2 or maybe WS2 all.
Is there any ongoing experiments?
I think I heard people are trying, but I don't know any. Yes.
You also mentioned that you want to measure susceptibility, magnetic susceptibility.
Right.
So presumably the position that very good whole phase is a ferromagnetic position, right? So would you expect the magnetic susceptibility to diverge?
So from Mott to QH.
from 120 to QH?
Oh, but you have external field. So you have external field and so okay. So my I think maybe you're asking this. If I look at spin polarization as a function of pi field, right?
No, I'm talking about actually the previous part of your talk.
The QH.
The anomalous.
Yeah, non so yeah.
So there, the transition just without the field, right?
Yeah. Yeah.
By key.
Yeah.
And there, SC appears, right?
That's right.
So it's not like a ferromagnetic
Transition, right?
So there must be some magnetic susceptibility there.
Oh yeah, sure. Yeah.
And is this in the experiment that?
Yeah. Well,
you might like agree that goes up at final temperature.
so I think the answer is yes. And let me show you the data. I have it here. I don't have a temperature dependent data. It's in sample size. Yeah, but I think so. What happens as a function of temperature, for example, you see that the MCD signal is 0 at high temperature, and then it onsets at low temperature. Yeah. So MCD signal onsets, which means that the slope will diverge, right? So I think I have it somewhere. Yeah, here. Yeah. Okay, you're right. Yeah. Right. This is MCD signal as a function of temperature in the quantum non-solid phase, and you see that it rises up below the temperature. And again, if you're in the quantum non-solid phase, if you look at the inverse susceptibility, it goes to 0, which means the divergence. Yeah. Now this is as a function of temperature. I think what we are asking maybe is as you approach the if you're at low temperature and you increase electric field from the module to the side. Yeah, I would love to see that data. I'm sure it's somewhere there, but it's not in the published version. Yeah. But you do see that in the model insulator, the MC signal is essentially 0. Yes.
What is the reason the superconductivity when you go system?
Yeah, so you're saying in the TMDs, yeah, that's that's even the big open question. We are all hoping to get superconductivity in the TMDs. Hasn't been found yet, as far as I know, experimentally. But yeah, but I think if I were to bet $1 on this, I bet it's just a matter of time. Yeah.
Theoretically, what is the difference between the external model and the chiral that is over model? I think.
Yeah. Yeah. Right. Yeah. Okay. Yeah. It's a good question. Yeah. Okay. Yeah. So I can say a few words. Yeah. So one obvious difference is bipartite versus non-bipartite. But in the cuprate, you start with a bipartite lattice. The magnetic order is a collinear AFM. While here it's this non-collinear AFM. So this could make a difference. So one thing we are playing with now is that if you go to the filling factor n equal 2, right? For a charge transfer insulator at filling factor n equal 2, you get a honeycomb lattice. Right, this I have it here. You get a honeycomb lattice, and the honeycomb lattice magnetic order is a collinear. Yeah, it's collinear AFM. Right. So maybe if you dope around filling factor 2, you can get superconductivity. Right. That's if you want to think about analogy with the cuprate, this could be a yeah. Say again.
You have to write that up now.
Too many things.
I have one question. So
did they already find something? Did your colleague already find something? I can't help. All right.
Yeah, I have a question. You have a Quadratic band.
Yeah. Right.
You have comments about possible
Right. Yeah, so it's a good question. Yeah, if you start with QH state, you dope it, what happens? Actually, there's beautiful work by you that showed that you can get something like a condo physics going on. Yeah, I think that's a very interesting question. Yeah, so I think there's also a paper from last night in the archive of experiments, right? That indeed show the doping. Yeah, these are all interesting questions. Yeah, I think the physics, the system seems to follow the magic. Yeah, even though it doesn't require a magic angle, it seems quite rich. Yeah, it's fine.
Yeah. Okay. There's a question. what sets the temperature of the announced power fixed? Is fixed the size of U in the Hubbard layer?
Yeah, it's an excellent question. You know, we have so far only done calculations at 0 temperature, but I think the most likely is not due to the U. U is probably much larger. Instead, the QH temperature is set by basically the spin ordering temperature. And the spin ordering, you know, in this case, you know, there are some doped electrons and some doped holes after charge transfer, right? So it probably is, you know, on the order of T, I would guess, something related to the hopping T. But we don't have it worked out yet. Yeah.
Terrell, you can unmute yourself.
Thanks. Yeah. So I have just maybe a few very remedial questions. I'm just confused about a few things. So the experimentally, is it easy to see the XY ordering in this canted phase you mentioned?
Yeah, that's an excellent question. So it's very hard. Yeah. So so I think this is actually a big open question that for magnetism. So you know, if you have a spontaneous SD correlation, right, you can observe it through the MCD, magnetic circular dichroism. But if you have a intervalley coherent state, which is what this XY magnetic order is, it's very difficult to observe it. Very difficult to observe it. And also, you know, the ordering temperature itself may be low. Certainly, in the case of WS2, WS2, you know, the exchange energy scale is only 0.1 millieV, and because of the triangle lattice is frustrated, the ordering temperature will be very, very low. So all this makes it very difficult to detect the XY magnetic order. So one thing we thought a little bit before is that if you have an XY magnetic order, you have a gapless Goldstone modes with linear dispersion. So this can lead to a magnon transport over a long distance. So something people in the community call spin spool fluidity. So one can maybe do some kind of a spin transport measurements this way.
I see. Actually, on that note, my second question was this is the counting. I was slightly confused. So in the 120-degree phase, there are 3 Goldstone modes, right? In your assuming I haven't actually fully understood all the symmetries. Maybe you have some anisotropies, but the usual 120-degree, there's no anisotropies. It's just there are 3 Goldstone modes. But in your quantum anomalous Hall side, is the Goldstone mode still 3 or they are less now? I was slightly confused. Is there
I cannot hear you. Is it Tyrone? I cannot hear you very clearly.
Can you hear me now?
Little, yeah.
Oh, okay. I was confused about. I was. Can you explain the counting of the Goldstone modes in the anomalous Hall phase?
So the anomalous Hall, well, it breaks a U1 symmetry, right? It breaks U1.
Right. So there's no other symmetry breaking. So the number of Goldstone modes are 3 and 1 on the across the transition. You go from 3 to 1. Is it true?
I think the number of Goldstone modes doesn't change across transition, right? Because in the XY, I mean in the XY magnetic order state, right?
Oh,
yeah, it breaks the spin one symmetry, and then in the quantum anomalous Hall state, you know, it still has this 120-degree magnetic order, but now it has a candidate SZ moments. So in terms of gapless Goldstone mode, the number doesn't change.
So the symmetries is just XY. It was not SU2 to begin with, just to make sure. Okay, I was confused by that. Okay.
The one I start with is, yes, this is because there's a, I didn't go into details. There's a spin-orbit coupling. There's a spin-orbit coupling. So, you know, even the modeling that I start with, the system only has SZ conservation.
I missed that. Sorry. Yeah. And my last question was about, do you understand the critical exponents in this, is there some understanding of the exponents at this transition or something?
Yeah, this is an excellent question. Yeah, this is a great question. So so this is as you can see, okay, let me try to find the slides. Yeah. So wait, this is right at the critical point between the mod and QH, and right here, yeah. Sorry, yeah. Right. So here, right at the critical point, you see that I have an interesting scenario. I have a linear dispersing direct band coexisting with a quadratic band whose bottom is also at the Fermi level, right? And in this case, actually, interaction is irrelevant. Interaction is irrelevant. So so you know, but on the other hand, you know, it consists of both, you know, z equal 1 degrees of freedom and z equal 2 dynamic exponent 1 and 2 degrees of freedom. So you know, I don't know how you call it, but it has this peculiar feature. Yeah,
I see. I see. So I see. So the interactions are in this sense dangerously irrelevant because
You
they
are
are
absolutely right. I wish I talked to you earlier. So we knew already more than a year ago that interaction is irrelevant at this critical point. But as you can see, it become relevant, marginally relevant after the band inversion. So for a long time, I don't know what to make of it. But recently, I talked to my colleague Max Malinsky, and he said exactly what he just said. This is called dangerously irrelevant. So in a classic example, he taught me is that if you have a XY magnetic order, right? This is some kind of magnetic anatropy is exactly like that. It's dangerously irrelevant. So if you have a fourfold magnetic anatropy, once you go into magnetic order phase, it gaps out the Goldstone mode and the system becomes massive. So just like here, right after band inversion, right, induction becomes marginally relevant. It opens up a gap, going to quantum non-solve phase, but it's irrelevant right before and at the critical point. It's dangerously irrelevant.
Sounds good. Yeah. Thank you for very nice talk. Yeah.
That's all. For the question, that's